It's similar to finishing electricity in AS, okay? You had like, particle physics, which wasn't that complicated, right? So they're recommended part of that, I think is like 85% of your syllabus. So we are done with capacitors. Capacitors are Kichurocom 9. I haven't done a math from the equation I taught you, so I'll just give you one question last to try out and ask you to mechanism start turbo. So yeah, this one last question from capacitors, okay? Right, so what I'll do right now is, since we have wrapped up capacitors, is I'll go through all the equations we have from capacitors, okay? So actually, so tell me all the equations that you have from capacitors. Let's start with the first one, which is this actual capacitance Baker formula. Right, so Q equals to CV. I don't know, shared column Tashne. Interesting.
So all this happened because you rejected our bribes. All this happened because you rejected our bribes.
Yeah, just
Sorry. Or is this so old-fashioned class. When was the last time you took a whiteboard class?
5 years back.
Were they as sleepy? Were they as sleepy?
Yes. It's nothing to do with the board. That's what I realized. Right, so let's see the equations one more time. Right, so Q equals to CV as the first one. And what's the one for energy stored in a capacitor? Half QV or half CV square or half Q square by C. So these are the ones that defines the properties of a charged capacitor. So it's, let's say, fully charged, you can apply these. But if it's not fully charged, you can't apply this, okay? Because that's in the process of charging, right? So then comes the transient equation. Transient equation is basically with time, right? So what's that equation for charge? Q equals to Q naught e to the power minus T by RC. And same V equals to V naught e to the power minus T by RC. And I is also the same thing. I equals to I naught e to the power minus T by RC. And I can think of tau, the time constant is equal to what? RC. What is the time constant tau? No. Like, what does it represent? Right, exactly. It's the time taken for charge, current, voltage to become 1 by E, the original value. So 1 by E, right? And there are some other equations out there. They're called the combination equations, how you combine your capacitors, right? So series and parallel. So how do you combine your capacitors in series? Yes, 1 by C total equals to 1 by C1 plus 1 by C2. And if your capacitors are in series, how do you combine them? Yeah, so C total equals to C1 plus C2 and so forth. That's it. These are all the equations that you have. Okay. All right. So let's look at the question here. It says a lamp of resistance 40 kilo ohm is attached to a 100 nanofarad capacitor that is charged. The voltage across it is 10 volt. Find the time taken for the energy or brightness to become 25%. So you want your lamp to dim down, right? Find the time taken for the brightness of the lamp to become 25%. So, try to. Get your ohm. Equations to the shall we? But you get rid of the nano in your calculation. This is nano, right?
We take nano.
Oh, fair. So whenever you do your calculation, you have to get rid of all prefixes. Time taken. 8 point. You have answer, anyone? Hint is that first you need to find out at what voltage your brightness is 25%. Find the voltage and then use that to find out how much time is taken. Chakurde, I want to start magnetism, but I mean, how can I move on from capacitor? You're an aparo. এখানে তো এনার্জি 25% হচ্ছে, রাইট? বাট এনার্জি তো কোনো ফর্মুলা নাই, সো তোমাকে হচ্ছে বের করতে হবে এনার্জি 25% হওয়ার জন্য ভোল্টেজ বা কারেন্ট এগুলো কি ভ্যালু হওয়া উচিত, এন্ড তারপর ওইটা দিয়ে হচ্ছে এইসব ইকুয়েশন ইউজ করতে হবে।
This is 5.5 millimeters. At 7.
How much? Yeah. Okay, Purdi, I think we spend enough time here. So আমি বলি কি করতে হবে এখানে, you have this lamp or হচ্ছে সব properties দেওয়া আছে, so it's 40 kilo ohms and it's attached to a capacitor. এটা হচ্ছে voltage হচ্ছে 10 volts দেওয়া, that's maximum brightness, and it's slowly going to dim down because the capacitor is going to discharge, so the bulb will start to dim down. The question is, how long do you need to wait for its brightness to become 25%? Brightness, which by the way I have already mentioned, is the energy of the lamp, right? What does the energy of the lamp depend on? So energy of the lamp is going to be based on, or the brightness is going to be based on what? The energy that the capacitor provides. So capacitor the energy that provide করছে ওইটাই তো তোমার brightness হবে, right? So the energy of a capacitor is what? Half CV square. এখন this value that you see here, this is the equation for what? Energy dissipated or energy stored? Stored, right? So energy stored হচ্ছে এখানে। এখন হচ্ছে আমাদেরকে বের করতে হবে that what should be the time taken for the value for the voltage, value for the energy to become 25%. So এটাকে 25% কমতে হবে। এটা 25% যদি কমে, as it goes down by 25%, right? Voltage should go down by how much? ওটা তোমাকে figure out করতে হবে। So how much should your voltage become for your energy to become 25%? So how do you do that? So we have done this before. There was a math I gave you earlier, এই same জিনিসটাই। So কি ছিল that energy is directly proportional to what? Voltage squared. So if your energy is E and your voltage is 10 volts, so 10 square, so energy যদি E by এটা কত হচ্ছে 25%, so how much should that be? Yeah, so 1/4, so E by 4, very good, should give you V square. And once you do this calculation here, you'll get a value for V. How much is that? 5 volts, I think. 5 volts আসে না? So 5 volts. Unitary method. আচ্ছা, যদি না বুঝে unitary method কেমন করতে আবার বলি। V square equals to E by 4 into 10 square divided by E. And from there we move on, and the E cancels out and everything else cancels out, and you get V of 5 volts. So you need to do your math and figure out the time taken for the voltage to go from 10 to how much? 5, right? So ওটার জন্য কোন equation use করবো? That equation, transient equation. So V equals to V naught e to the power minus t by RC. V is 5 equals to 10 e to the power minus t by R is how much? 40 into 10 to the power 3 into C হচ্ছে 100 into 10 to the power minus 9. So এখান থেকে t আসে, এই t টা কত আসে? That's it. So this part is the voltage. I'll write down what this means. This is voltage when energy is 25%. Yeah, but the problem is you don't know Q. Q equals to. Then how do you find the V? You found the V separately. No, I don't think it works that way. So you are going to use Q and V to find energy. V is what? 10. Acha, our Q is the original charge, and you find the energy, and you divide the energy. I mean, you take 25% of the energy, and then what do you do? Oh, then it'll work. I think you should get the same voltage. Yeah, because QV doesn't work. I've mentioned this before. Can anyone remind me why can't we use QV? Or why shouldn't you use QV in these kind of questions? Yeah, it's actually when your energy is changing, both Q and V are changing, neither of which you know. But if you do half CV square, what is C? Constant, right? So therefore the V and the E are related, so it's easier that way. 25% of it. Yeah. Okay, anyways, let's move on. So we will be starting our next topic, which is magnetism. So magnetism did to idea dito, okay? এখানে হচ্ছে sometimes ওরা লেখে, in this case I don't think ওরা লেখছে মনে হয়, but you need all of your O-level knowledge first before we start, okay? O-levels গুলো পারলে then we can start here, because O-levels কি লাগবে? Everything. Because the reason I'm saying that is because this chapter, this entire topic is the exact same thing as your O-level with one addition only. We're going to do the math of everything. So O-level, say, if you remember the right-hand grip rule, the Fleming's left-hand rule, the Fleming's right-hand rule, induction, EMF, everything is the same, nothing new. In fact, I'll be giving you those notes right now. O-levels will our people. But we can get you quantify করতাম না. If you remember, O-level say magnetism was famously known for not having any math. The only math you had in magnetism was a transformer ratio. আর কিছু ছিল না. One chapter in the entire O-levels, কোনো math নাই. That will come back now. Okay, so now you have only math here, nothing else. So yeah, the chapters that you see here, you know most of them. I mean, can they start already? So you know that there's something called the motor effect, right? So motor effect is this one. Okay, so they don't call it a motor effect, they say force on a current carrying conductor, which is essentially motor effect, right? And then we find the formula that is needed for motor effect or force. So now we can actually find FBI mode, what is that F, the value of it, okay? Then this one, the force on a moving charge, eta is a little new, and a topic is a little bothering because there's some strange topics here, like the Hall probe and the Hall voltage and everything. Eta is like, I would say, new. This again is something you have done before. Magnetic field due to current is the right-hand grip rule, right? So ওগুলা থাকবে এখানে। এটার পরে there's another smaller topic here. This one is magnetic induction. This is basically the Faraday's law of electromagnetic induction, and there was something called the Lenz's law. If you remember Lenz's law, so Lenz's law and everything will cover back for a bit. So yeah, that is your magnetism. It is actually a very comprehensive topic. এটা শেষ হয়ে গেলে আমি বললাম তো this first book is actually 80% of your syllabus requirement, so এটা হয়ে যাবে, but এটা শেষ করতে হবে আগে আমাদের. Okay, so I'll start from the scratch here. I'll move around a little bit here because হচ্ছে sequence ঠিক মতন দেয় নাই. So I'll first do this one. 20.1. So what do they want us to know? Understand that magnetic field is an example of a field of force produced by a moving charge or permanent magnet. Represent a magnetic field by lines. So magnetic field lines draw করা এখানে শিখতে হবে. And the other thing that I'll be doing here is actually, hopefully I can do them. Sketch magnetic field pattern due to current in a long straight wire, flat circular coil, and a long solenoid. So it's magnetic field pattern draw করতে হবে. Understand magnetic field. So if you place like a iron core in a solenoid, it becomes a stronger magnet. So that is there. And yeah, so these are the things we're going to do today. Okay, so we'll go back to our O-levels. But before that, let's first try to understand what a magnetic field is and what are some of the examples of magnetic fields that we have. So what is a magnetic field? I'll just remind you what an electric field is, what a gravitational field is, then see if you can answer. Okay, gravitational field is a region in which mass experiences force. Electric field is a region in which a charge experiences force. Magnetic field is a region in which magnets experience force. So from O-levels, you knew it was just magnets, and then that's where you had the plotting compass. So O-levels said the definition of a magnetic field line কি ছিল? The direction in which a plotting compass pointed. I think that one still holds. Like, when you draw the magnetic field line, right? What is that direction actually indicating? It's which way the plotting compass points. So do you know what a plotting compass is? Okay. So এখন, what's the origin of magnetism? So magnetism, it's a very strange topic. Okay, it's still not fully understood, like right now after all these years, right? So let's try to understand the basics of it. So basically what we know so far and what we need. So we understand that there's this material called a ferrous material. This material is made up of some kind of combination of iron, and this material has the ability to demonstrate what around it, a magnetic field. And as we start to go in to figure out why does it do so, we find that it's due to the presence of these very small magnets inside them, which are called the domains or dipoles. Okay, dipoles, domains is also another word they use. Okay, so what are these domains and dipoles? They're basically small units of magnetism. Question is, where did they come from? Because they're the reason why your what is magnetic in nature, iron, right? So their origin So their origin is the part that we are still not sure about. Okay, I mean, we know about it, but we just know it as a fact. We can't really explain properly. So the origin of magnetism, right in the subatomic level, comes solely from one particle. What is it? An electron. So একটা electron থেকে magnetism arise করে, and not only just the electron, the what of the electron produces that? The spin. So it turns out electrons actually spin, and there are two types of spin out there. So one spin is the spin that it does on its axis, and this spin results in the formation of poles, as we know. So there's a property generated around it on the top and the bottom. The properties eventually lead to attraction and repulsion. We started calling this the what pole? The north pole, and we started calling the one at the bottom the south pole. It is actually not this though. I mean, this is like a very dumbed down version. Okay, as you go further, you'll learn that spin itself is a very complicated property of particles, which you haven't learned yet. But understand that when they spin, they produce this north and south. Now, if they spin the other way, what will they do? Kind of natural. Yes, the north and south will get what? Flip. And there's this Pauli's theory. Do you know what that is? From chemistry, Pauli, Pauli. No? Exclusion theory. No? That in a particular shell, you can't have two electrons spinning in the same way. So what do you call that? Huh? Achha, okay. Yeah, you don't grade the person who actually found it. Achha, okay, fine. Yeah, okay. So, Paperna, spin pair repulsion theory. Achha, okay, that's what it is. Anyways, So these spins that you have here, they result in like a north on the top and like a south at the bottom, or sorry, north at the bottom. And when these electrons are paired up, they generally cancel out their magnetism. So shells glow structure kora thake. However, iron has an anomaly, and we learned that generally speaking, iron is very strange. On the nuclear physics, it has some odd properties. So iron one of the pairs actually keep pointing in the same direction. It actually defies the exclusion principle. Pair repulsion So iron has this behavior. And because of that, what happens is in iron, right? This is typically in every other element. In iron, you end up having the north and the south remain as net. You'll end up having what here? A north pole and a south pole as a net. Net can bolte se because overall there's a north and a south. North and south in the shop exists, but what happens in most places cancels out, right? And this is the origin of magnetism, but there is a catch. This is the origin of the ferrous magnetism. What's the ferrous magnetism? Is the magnetism demonstrated by what? Iron. So we iron, nickel, cobalt. There's this part in the periodic table. They show magnetism, and that magnetism is due to this anomaly in their structure. But then we found that the electron is actually original, source of magnetism, and electrons are everywhere. Like, if you think of a delocalized shell or delocalized electrons of metal, right? There are plenty of electrons out there. So why don't we see magnetism in, like, let's say, the metal here? There should be magnetism, right? So it turns out the electrons are always moving around in a manner that their spins are what to each other. Yeah, they canceled out, right? Because, they're opposite to each other. However, we found that you can actually make the electrons all spin the same direction in a wire. To do that, what you need to do is, so that's the delocalized sea of electrons out there, and sea of electrons like that around it. You can make the electrons all face the same direction and spin the same direction. How? Bring a magnet closer to it, but this is not a metal. What was it? Solid. No. Question in a typical metal, random metal, okay, any metal for that matter. Yes, correct. In any metal, right? How do you make all the electrons face the same direction, spin the same direction? So the answer is by passage of current. So the moment current passes through your wire, it by definition makes all the charges move in what direction? Same direction, and they just start to spin the same way, and no one's actually canceling each other out. As a result, the first time we saw the spin as an amplified part is whenever a current flows through a conductor, there's a what generated around it? Magnetic field, right? And that magnetic field is nothing but amplification and representation of the magnetic field of individual electrons. So প্রত্যেকটা electron ছোট magnetic field থাকে, and they're all going the same way. They all add up, and as a consequence of that, it creates that big field around it. And that big field is basically the representation of the field of a single electron out there. This is how you produce a what magnetic field. But who's responsible here? Moving charge. Okay, so moving charges do this, and we eventually found that positive charges can also do that. So if you have some positive charge out there, they can also create this effect. Okay, so it's not just electrons out there, it's charged particles. Proton because protons are not typically found isolated and moving around. But if you can isolate a positive charge, like a helium nucleus, which we call the alpha particle, it will also do the same thing. So magnetism eventually boils down to two things. One is something that is what in nature? Ferrous. Ferrous manochiki, it has iron in it, or it is something that's moving and charged. So what's the definition of magnetism? Magnetism is a magnetic field, is a region in which a ferrous material experiences force, and who else experiences force? A moving charge. Our syllabus primarily deals with the moving charge. We don't go to the ferrous part. Ferrous part, it's not very, I would say, universal. It's just one piece of rock showing magnetism, right? So we go more for the current. Current is better. So yeah, that's it. Now, how do we question? Is not. Oh, that we don't know. That is just still a mystery. So it's something to do with quantum mechanics, and which I know is not well defined. We just know that electrons, when they spin, they produce this effect around them. That's all. Huh? Tiny planets. That's 100% possible. I mean, the latest theory is that we're in the singularity of a black hole. So, I mean, you know. No. It's just one of them. The second last one. Like অ্যালুমিনিয়ামে মাঝে মাঝে হয় না লাস্টে হচ্ছে 9-1 থেকে 10-0 হয়ে যায় SPDF no so there's some anomalies out there structurally. So aluminum has one shell balancing করার জন্য. It's basically trying to find the most effective and most stable structure out there. Iron, it turns out that exclusion না করে it becomes stable. In fact, we'll learn eventually iron is the most stable nucleus in the entire universe, and we learned this in O levels. Do you remember where? Yeah, the core of a star. The core of a star undergoes nuclear fusion, and the moment the star dies is when what starts to fuse? Iron. Because once iron fuses, it's stable. Nothing wants to go forward from there onwards. Anything. So I can create magnetism out of any moving charge. So if electrical impulse passes through your body, right, it produces a magnetic field around it. So our body is magnetic in nature. Yeah. Right. So now let's try to visualize magnetism. So it ja bolche getting into O-level stuff. Like we have done this in O-levels. So এখন হচ্ছে what we're going to do right now is how to quantify it. Quantify মানে হচ্ছে numbers দেখে বোঝানো যায় how strong or weak something is. So এটার জন্য the first thing we're going to learn is how to draw a magnetic field. So if I have a magnet with a north and a south, this is your north. I'll start with things that we are, aware of. Then I'll show you different structures out there. So this is the north of a magnet, and then you have the south of your magnet here. A magnetic field will be generated here. Can you tell me what's the shape of this magnetic field that's generated here? Yeah, it's going to be lines that go from north to south, right? And এই লাইনসগুলো কি represent করে? এই লাইনসগুলো represent করে হচ্ছে কোন দিকে? If you place a plotting compass here, they would have pointed. Okay, so can anyone tell me what's a plotting compass? Yeah, it's just a small arrow, right? And the tip of the arrow is a what pole? A north pole. Okay, so yeah, that's how your magnetic field looks like. Now, a magnetic field question থাকলে বলো আমাকে if you have any. Electrons north pole faces. In the direction in which the electrons north pole faces. No, এটা বলা যাবে না. Because this is north, and you have an electron. I mean, that defines it, but we generally don't define fields with things we can't see. So এখানে তো হচ্ছে electrons it'll actually move that way, right? But we can't really see the electrons north pole to begin with, so we can't use that as a reference. So easier reference to use something that you actually have with you. What is it? A plotting compass, right? So plotting compass, you have your north pole here. So if I take this here, you'll see that it'll spin around and go like that, right? So that confirms that that's the north pole. Right, so that's the field here. Now, field can quantify kora. So there are two things I'm going to teach you right now. Listen carefully. A2 starts here. So these lines are referred as magnetic field. Just field bola hoy, field lines bola hoy. So field line we use a symbol called phi. And phi hoche magnetic field or magnetic flux. The word I'll use very often. Flux, field, interchangeable, okay? Magnetic field line, and that's phi. And phi has a unit which is Weber, WB. Okay, that's Weber, WEBER. It's the person's name. So Weber is the unit for magnetic field, just like a fielder and value. But there's a problem in using magnetic field to define the strength of a magnet. I'll show you right now, Cano. So you see these lines here, right? Each of them represent one value. So what's the total value here? Like each of them is 1 phi or 1 Weber, sorry. So 4, right? Now I can take this and I can do this here where I have these lines and they are, far apart. And if they're far apart, the total phi that you have here is also 1, 4, right? But in terms of strength, and you know this, I think by diagram, field lines can have the same logic in every chapter. the concentration, direction, and everything, right? So can you tell me which one is strong and which one is weak? Yeah, so the upper one is a strong field, and it's strong and what as well? Uniform. Achha, so uniform. And nicheta hoche uniform, but what is it though? Weaker compared to the previous one, right? So this is a weaker field out there. But if you look at the value, this is important, actually carefully, you know. If you look at the value of it, they're same. What's the value for the upper one? 4 Weber, nicheta 4 Weber. So it's like comparing mass to compare material. So if I take 1 gram of metal and I take 1 gram of let's say air, right? Just two or 1 gram. Can I just say that air is a metal? No, but they have same mass though. Why is that argument flawed? No, so I take one question to I take 1 gram of metal, I take 1 gram of air, and I say that they both have same mass, so hence they're the same thing. Refute this. Tell me why is this wrong? ওটা তো আমি বলছি, but আমি তো বলছি যে like we know it's air and this, but I took 2 random things out there, they have same mass, right? And I go like they're the same thing. Why are they not the same thing? Yeah, I mean, that's for you to find out. Yeah, so আমি যদি তোমাদেরকে দেই that 1 gram of metal is like a pinch in my hand, right? And that 1 gram of air is like a handful, right? Can I now say that they're the same thing? No. So there's a very important factor that we ignore: volume, how much space they occupy, right? No, you're right. It's density eventually. So eventually, I'm key compare kori, not mass, but the mass per unit volume. Similarly, we don't compare their phi, we compare the phi per unit area, right? And we come across this new quantity which is called পুরোটাকে নিয়ে করা হয়, this entire thing here, the strength of a magnetic field. This is called magnetic flux density. Okay, so magnetic flux density, I'm কেন এই analogy use করলাম, it uses the same logic, because magnetic flux density. So instead of finding magnetic flux, we'll find magnetic flux where? In a particular, not volume, very good, area. Why? Magnetic field is 2-dimensional. There's no volume to it. It's in a plane. So this is magnetic flux density, and this is going to be represented by the symbol B. B is the symbol, and এটার unitটা হচ্ছে Weber per meter square. So WB per meter square, but we convert that and we have a derived unit here called the Tesla. Okay, so Tesla is the unit for magnetic flux density. So B and phi, these are the only 2 things we have. Okay, now how do you relate them? I think you can figure out the equation yourself, but I'm bole dichi. So B, magnetic flux density, must be equal to what? Yeah, it's the amount of magnetic flux per unit area. So phi divided by A. That's it. Okay, and that's the first equation we have in our syllabus. So it's called magnetic flux density. Is it okay? So it compares the strength, right? So if you want to compare the strength of 2 magnets, would you compare their phi or would you compare their B? B. Okay, I'll give you more examples. It's actually very interesting idea. So the Earth, for example, do you know what the magnetic flux density for the Earth is? So Earth is a magnet, if you didn't know, right? It's a very big magnet, right? But is it a very strong magnet? So it turns out it's not. It's one of the weakest magnets out there, right? So আমাদের Earth এর magnetic field lines গুলো এরকম করে বের হয় North Pole থেকে. And if you find the strength of our Earth's magnetic field, it is 0.5 millitesla. Okay, so how strong is that compared to other things out there? Why am I doing this thing? I'll explain. I want you to understand comparative values of magnets. যে কোনটা strong বলা হয়, কোনটা weak বলা হয়, and you'll find something surprising here. This is the magnetic field of the Earth, right? It's fairly weak. How much do you think is the magnetic field strength of a bar magnet that ওই refrigerator use করা হয় না, magnet গুলো ছোট ছোট black color, ওইটার strength কিরকম হতে পারে? 50 Tesla. আচ্ছা, very ambitious guess. 20 20 millitesla, so that's actually not bad. So it's actually 10 এর মতন হয়, 10 millitesla, 20 আমি নিব, is not bad. So that is it. So now comes the strongest magnet made by humans. How strong is it? So the strongest ever magnet, one of the strongest, এটা হচ্ছে কোথায় আছে আমি বলি, is used in CERN. So there's this thing called particle accelerator, Geneva, Switzerland, ওই জায়গায় CERN. They have made the strongest magnet out there, particle acceleration করার জন্য. That is a massive 2 Tesla. Okay. CERN হচ্ছে একটা experiment to find particles like quarks and leptons. Particle accelerator বলা হয়. So 2 Tesla. Okay, so 2 Tesla create করার জন্য you need extremely high current and very sophisticated equipment. CT scan এ, so CT scan এ magnets use করা হয় না, তুমি যেটা ভাবছো MRI তে কাছাকাছি. MRI is 1 Tesla. So MRI machines are very strong. MRI রুমের ভিতরে কিন্তু if there are metals out there, they'll just fly around because of the strength of that thing. If you have metal in your body, right, it'll rip your body apart. It's very strong. A chance needed. So if you have like tattoos, you can't really do MRI because the tattoo uses metal. The metal sometimes is iron, and it'll just come out of your skin because it's that strong. Okay. They don't. No, actually, they don't. The Earth, no, it's not a strong magnet. It's a very large magnet. That's why the strength, the field is very wide. But in terms of strength, it's so weak. It doesn't deflect anything. I have a plotting compass here. Or a plotting compass. Yeah, but right now, yeah. So this one is your typical horseshoe magnet, right? It also 10 millitesla. It's very weak. That's why it barely picks up any pins out there. So it's there, right? So yeah, and that one. This one is probably 5 millitesla or something. Very, very weak. Achha, anyways, let's move on. So are you clear about the equations and everything? Right, so this is the introduction to magnetism. This is how we quantify it. But there is obviously catch for everything. এখানে একটা catch আছে. So B is magnetic flux density or magnetic field strength. So দুইটা word আছে বুঝার জন্য. I mean, different schools and different teachers use for different terms. আমি দুইটাই বলে দিচ্ছি. একটা হচ্ছে magnetic field strength. This is more aligned with electric field strength, gravitational field strength, or you can also call it magnetic flux density. Magnetic flux density is more literal in terms of what it is. It's the density of the field, right? Magnetic field flux density and area. Now, at the problem, it is bully. A question is deceiving. Use for easy, but it's not. There's a problem. So the problem is that imagine you have this surface here, and there are field lines coming out from this surface. So it's like a table, and the field lines are coming out from the table at an angle like that. So each of these field lines, they have a value of 1 Weber. Remember these lines here? Same line, okay? So that is it. Now I want to find the strength experienced by this region here. A region of the magnetic field strength. So jeta korbo is I'll divide the watt by watt, the phi by the area. So you can have phi charta. So what's my total phi value? 4. So these I'm doing this to show you like it's 3-dimensional. It's coming out of the table at an angle. Like imagine this, right? Like that. So it's not watt to the table, perpendicular. So yeah, the lines are coming out like that. Now you want to find the strength here. So what would you do? You would multiply, you divide phi divided by the area here. Unfortunately, you can't do that. Because the rule is, in order to find the flux density, the field lines, right, have to be what to the area, perpendicular. Okay, so breakdown korte hobe, and turns out magnetic field is obviously a what? Vector. So আমাকে এটা যদি breakdown korte hoy, what would be my vertical component here? Yeah, so the vertical components that you get here, these would be all phi sine theta, and then that you can use to do your math. Okay, so be aware of this. They'll give you questions where it's at an angle. তোমাদের just যেটা করে নিতে হবে perpendicular টা বের করে নিতে হবে before you can apply the formula. This is like this area overall. Okay. So yeah, এটা আমি পাশে অ্যাড করে রাখলাম. So এটা হচ্ছে that phi must be perpendicular to the area. Electric field or magnetic field. The lines come out perpendicularly. That's how we draw it. But to calculate it, you have to take the area that's perpendicular for the formula. Okay, so I'll give you notes on this. These are like all definitions and everything. Basic idea. So one more time, magnetic field, just the field is represented by phi. The strength of the field is represented by B, and B is phi by A. And to find the B, you need to make sure your field lines are what to the A? Perpendicular. Okay. Now let's move on to the next part. So আমি তোমাদের কিছু question করব with hope of answer. So দেখি টাইম আছে দেখুন আর 10 minutes বাকি শেষ করে ফেলি so yeah, magnetic field patterns and direction. Now my aim is to wrap up the first magnetism bit before your school exams and everything. So induction to maybe I'll try, but first part ta hoye jabe asha kori. Right, so let's start. Magnetic field patterns and direction, all of them. Let's start with the first one that we learned, that when you have a current carrying conductor, there's a magnetic field generated around it. Ask, I give you a background to it. They'll never ask you in your A levels, why is it like that? But I give you the reason. What's the reason? What's going through it? Electrons. And the electrons have their own field. Or field merge kore, and they create the whole thing, right? Eta hocche ami jigesh korbo individually, okay? Because I need to understand where are you individual in terms of your understanding. Right, so I'm doing this chapter with the grade 9 batch class potential. Okay, so you have this current carrying wire here. I'll start with Talha. Can you tell me what is the pattern of the magnetic field around this? Shape, I don't want direction or anything, just I mean, what would I see? Current pattern circles. Acha, okay. One step further, can you tell me whether they are concentric circles or just random circles? Do you know what the difference is? Concentric one একটা common center থেকে বের হচ্ছে. Acha, do you think they're separated by equal distances or different distances? Equal. So the further I go, the separation of the field lines would be all equal. That's very good, and that's because strength coincidence. Acha, right. So this is how the pattern is. Now we know that this is not the best way to look at it, because it gets distorted because of the perspective. You're looking at an angle, right? You'll find that they appear to be of what shape? Ovals, right? So why we don't follow this particular view? Because it distorts the shape for us. It looks like they're oval, right? But they're not. So which view would be better? Top view, right? So top থেকে যদি দেখি, now it's where we actually come. So top view তে যদি দেখি, এখানে যদি plus হয়, এখানে যদি minus হয়, how would you show the current in this wire if you were to look from the top? এটা একজন answer করবে, তুমি বলো। Current কি দিয়ে represent করবো? এই যে এখান থেকে তুমি উপর থেকে তাকাচ্ছ ওয়্যারের মধ্যে, ওয়্যারের ভিতরে তো কারেন্ট আসছে, কারেন্টটা কোন একদিকে যাচ্ছে, ওটাকে আমি দেখাতে যদি চাই on a paper, what do I use? How do I symbolize it? Arrows. আচ্ছা এই যে একটা ওয়্যার আছে, there's current in this wire, right? আচ্ছা তুমি উপর থেকে তাকাচ্ছ ওয়্যারের মধ্যে, কারেন্ট তো দেখতে পারবা, ওটা কেমনে দেখাবো কারোকে? Arrows, আচ্ছা। Do you know how? Yes, exactly, a dot or a cross, right? So এখানে হচ্ছে, as you look from the top, would it be a dot or a cross? Can you tell me? Yeah. Right. So do you know what dot and cross is? Yeah, dot is in or out? Out. And cross is in. How did they figure that out? Yeah, so it's if you forget or you don't know what this is, it's a very easy way to remember. So think of an arrow, like a bow and arrow. So you have this arrow here, right? At the tail of the arrow, what do you have? Yeah, your feathers, right? ওই feathers গুলো হচ্ছে এভাবে করে ডিজাইন করা থাকে that when you look at it from the cross section, it looks like a what? Cross. মানে যে if you're looking from here, you'd see a what going away from you, a cross. And if you were looking at it coming at you, what would you see? A dot. So whenever something's coming out, right, of anything, a page, for example, we see the tip of it. So we see a dot. If it's going away from you, what would you see? The tail of it. What would that be? Cross. So in this particular scenario, the current goes from plus to minus, right? And it's coming out like that towards the person's eye. Would you see a dot or a cross? A dot, right? So you can dot that vector. And the dot is a universal thing. It's not just magnetism. If you want to show in and out in any kind of scenario, you can just use a dot, right? Now, the pattern would be a bunch of circles here like that. And circles go kache thakbe, and they'll start to what? Get further out, because what happens to the strength of my field? Decreases, right? So, question for clockwise or anti-clockwise? The field lines. Anti-clockwise. Do you agree? Anti-clockwise. How do you find it? Yeah, so it's called the right hand grip rule. You take your right hand, the thumb represents the direction of current. The current is coming out of the page, right? Like that. And you see which way your fingers naturally go. Your fingers naturally will follow that direction, like that, right? So that is what? Anti-clockwise, right? So এখানে anti-clockwise. And naturally, উল্টা দিকে যদি যায় তাহলে কি হয়ে যাবে? মানে if the current was across clockwise. So this is how you find the magnetic field pattern around what? A current carrying conductor. Is that clear? Okay. Now, there's something else that I want to do. Just quickly, I'll take 1 minute for this. You have this thing in the next class, I have to better buchhabo, but if I take a wire and I wrap around the wire, আচ্ছা মানে আমি ওয়্যারের চারিদিকে ঘুরে এসে এভাবে যাই, it forms a shape. What do you call that shape? Solenoid, right? So solenoid কিন্তু the name of a shape. The shape মানে হচ্ছে a structure. So this is called a solenoid. এখন এই solenoidটা যদি হচ্ছে ভিতর দিয়ে current pass করে, something happens. Something very interesting happens. What is it? Yeah, so magnet is what? Poles pointing. Which chapter are you in? Yeah, so এই যে এখান থেকে হচ্ছে কারেন্ট পাস করতেছে, কারেন্ট যেহেতু পাস করতেছে, আমার এখানে হচ্ছে this something happens. My question was what happens? Right, so what happens is every single coil here produces a magnetic field that looks like this. Flat coil টা আমি তোমাদের পরে দেখাবো. And because of that, you'll find that from one side কি হচ্ছে? From one side you have a lot of field lines coming out, and এই field lines গুলো ঘুরে অন্য সাইডে এসে কি করতেছে? Enter করতেছে. So what would you call a place where there are a lot of field lines coming out? Yeah, that's actually not wrong. Yeah, it's called a pole. But which pole to be in particular? A north pole, right? So solenoid, I mean, a question before you guys leave. Is solenoid a magnet? No, it's not a magnet. That's actually right. What is a solenoid? Temporary magnet, yes. Huh? Yeah, it's an electromagnet, but the thing is that if it's not a magnet, what is it actually? Why is it showing magnetism? Acha, so that's actually the closest answer. So the correct answer is a solenoid, right, is basically just a coil carrying current, which produces a magnetic field, which just happens to mimic the exact same magnetic field of what? A magnet. So there's nothing about a magnet here. Just the field here resembles what? A magnet. And that's why we have this thing. It's called a temporary magnet, electromagnet, whatever you want to call it. But it's basically mimicking a magnet. Okay. Anyway, the next class, and then we'll look into more A2 stuff.